Hello, this is Jesse Mason from Teach Me with speed versus velocity. These two terms are used interchangeably in today's popular vernacular, but in the scientific realm they have different, and of course more precise, meanings. In this video we'll delineate speed and velocity by way of an example. So in my hometown of Ypsilanti, as in many other cities in the States now, a yearly running event is held, titled the Color Run. The Color Run is aptly billed as the happiest 5K on the planet, and if you've ever attended a Color Run, then you know what they're talking about. Color runners leave the starting line in an old part of Ypsi known as Depot Town and proceed to jog around the city in a jagged loop. First they head east for a block, then north for a few blocks, and then they turn west. At this point, the runners celebrate the completion of their first kilometer by getting doused with colored cornstarch. Now, typically people dislike getting stuff thrown in their faces, but at the Color Run, it's literally a rite of passage. Next, the runners turn north for a few blocks, hit the second so-called kilometer color zone, where another monochromatic dousing ensues, before turning south and jogging along my alma mater, Eastern Michigan University. After a few blocks, the color runners turn west and jog past the dorm where I met the woman of my dreams. Then they head south, then east, through another kilometer color zone, before heading south again. Unbeknownst to runners, the next turn puts them on an ancient mastodon trail, now paved, populated, and pronounced Michigan Avenue. Runners turn north off of Michigan Ave, hit their last kilometer color zone, then proceed for several blocks before their final turn, which leads them down to a riverside park. Here, instead of a 5th kilometer color zone, runners are treated to a massive dance party, where, of course, colored cornstarch is peppered on them like confetti. And that is the Color Run. So, we're going to determine a particular runner's average speed and average velocity for their run, but before we do so, we need to understand the difference between two more fundamental quantities, distance and displacement. Distance is simply the length of the path traveled by the body in question. In a car, distance is measured by an odometer. Now, the Color Run is a 5K race, that is to say, the length of the path traveled by the race's participants, from starting line to finish line, is 5 kilometers. We'll write this in SI units. Final distance, d sub f, equals 5,000 meters. Of course, if the final distance is 5,000 meters, that would imply that the initial distance, d sub I, is 0 meters. Implicit in these distances is the location of our origin, the starting line. We'll mark that on our map. And while we're at it, we'll indicate our coordinate system for the map, which is to say, we'll mark the direction of north. Now let's look at displacement. Displacement is defined as a change in position. Change in position relative to what? Well, relative to our origin, of course. So what is the initial displacement? Again, because our initial position coincides with the origin, the initial displacement is 0. So S sub I equals 0 meters. Don't worry about that tiny arrow over the S. We'll get to that in just a moment. Now, how about our runner's final displacement? Well, the final change in position of our runner relative to the origin would be the length of a straight line drawn from the origin to our runner's final position, the finish line. We'll draw an arrow from the origin to the final position to represent final displacement, S sub f. The length of this displacement is about a quarter kilometer, so we'll write S sub f equals 250 meters. SW, which stands for southwest. This last part, the direction, is a critical difference between distance and displacement. You see, displacement is what we call a vector quantity. A vector quantity is a quantity endowed with both magnitude, in this case 250 meters, and direction, in this case southwest of the origin. We indicate a vector quantity graphically by drawing an arrow, the length of which represents the magnitude of the vector. A vector is indicated mathematically, you guessed it, by drawing a tiny arrow above the variable representing the vector. Distance, on the other hand, is not a vector quantity because it lacks directional information. Distance is what we call a scalar quantity, a quantity describing magnitude only. Great. Now we can turn our attention to speed and velocity. Let's suppose that our runner leaves the starting line, traveling eastward at a couple meters per second. We'll indicate this motion with an arrow. This arrow, like the displacement arrow drawn in green, is a vector arrow, and it represents the magnitude and direction of the runner's instantaneous velocity, or velocity at that instant. Since the magnitude and direction of the runner's instantaneous velocity change throughout the race, we'll traverse the course indicating different velocities for the runner. Notice that the second velocity vector arrow is shorter than the first. This implies that the runner is moving more slowly at the second position. So we'll indicate a velocity here and here. Of course, there's an infinite number of velocity vectors we could indicate. We're just drawing a few. And maybe our runner is getting tired after the first couple clicks, is beginning to slow, so shorter vector arrows. Maybe even comes to a halt at the 4th kilometer color zone to rest, replenish some electrolytes, clean the cornstarch out of their ears, and runner goes on to complete the race with a finishing time of, let's say 1 hour. Now we can determine average velocity. The average velocity of a body is defined as the change in the body's displacement, delta S, divided by the change in time, delta t. Expanding, we get S sub f minus S sub I over T sub f minus T sub I. Here the initial displacement is 0, so we can set this value to 0. And almost always the clock starts at 0. Here it's implied by our final time of 1 hour, so we can set T sub I to 0. Good. Now we'll insert our values for S sub f and T sub f. So for S sub f we have 250 meters southwest, don't forget the direction, and we'll convert 1 hour to 3,600 seconds for T sub f. This puts our velocity in the preferred SI units. So this implies that our runner's average velocity is 0.07 meters per second southwest. That's only 7 centimeters per second. A tortoise is more than twice that fast. Is our runner really that slow? Well, let's take a look at average speed and then come back to this question. Average speed is defined as a body's change in distance divided by the change in time. If we expand this expression, we get d sub f minus d sub I divided by t sub f minus t sub I. Again, the initial values are both 0. For final distance, we have 5,000 meters, and again, final time in seconds is 3,600. This implies that our average speed is 1.39 meters per second. Pretty pokey for a so-called runner, but it seems much more reasonable than the snail speed value we got for average velocity. So what's the difference? The difference is in what these two quantities are describing. Speed simply describes how fast a body is moving, irrespective of direction. If we incorporate direction, now we're talking velocity. If the motion's nonlinear, the average values for speed and velocity are going to be different. Velocity is, yes, you guessed it, a vector quantity. It describes both the magnitude and direction of our runner's motion. Speed is a scalar quantity and contains no directional information. And that's the difference between speed and velocity. I'm Jesse Mason. I hope you found this video helpful. There are more like it on my channel and more on the way, so click subscribe to stay tuned. If you'd like to make a suggestion for future Teach Me videos, or just want to say hello from your part of the world, please feel free to do so in the comment section below. And as always, happy learning.